is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hello and welcome to SkyTour Radio here on KGRAradio.com. I'm your host, Mark D'Antonio, here with my wonderful and industrious co-host, Amanda Curran. Hello, Amanda.
Hi, Mark Hale.
And we want to welcome you, our KGRA family, to the broadcast. Now, a couple of announcements really fast. We want to introduce a new feature. It's called the SkyTour News, which is a weekly compendium of famous events in astronomy, the UFO world, and space that took place on our current show air date throughout history. It'll be a really fun vid to watch. You can find that you can find the SkyTour News on the SkyTour Livestream YouTube channel. And don't forget to subscribe and hit the bell once you do to get notified when any events, such as a new SkyTour News is available or a SkyTour Livestream is starting. That'll be fun. Lastly, at our online store at fxmodels.com or at the Planetary Replicas page on Facebook, if you choose to purchase anything between now and next Wednesday, you can get $15 off if you enter the code SkyTour15. That's SKYTOUR 15. That'll happen during the checkout in the store, and you'll get a $15 discount on whatever you purchase. Now, links are on the SkyTour Radio page at kgraradio.com. So tonight on SkyTour Radio, it's the universe of stars and the possibilities for extraterrestrial life. I mean, that's going to be exciting, I hope. So it's all going to be told and examined through the eye of science. And I think that if we look at this from that perspective, it'll make more sense to a lot of people, especially those who don't really understand a whole lot about the stars. Now, we want to look at the different types of stars to see which ones can support the planets and possibly life. Now, in our galaxy, we have up to 400 billion stars. Now, that's a high-end estimate, and we really don't know for sure. But we are in the galaxy, so it's kind of hard to count the stars in our galaxy. It's like counting the trees in the forest, but from inside the forest. You can't really do it because at some point the trees block the distant forest beyond. So it's the same for us. Yeah, we can count the stars and make good estimates in other galaxies, and so by comparing those galaxies to what it looks like ours is, we can kind of get a rough estimate. So the truth is we have star-wise between 100 billion and 400 billion stars in our galaxy. Now, of those stars, there's a high-end estimate, and it's very high-end, that up to 10% of those could have habitable planets. That is, planets that can support life like us. All right? Now, we're going to explore that a little bit tonight, and we're going to have some fun with that. Now, I want to go and first of all, take you through this logically, and I think the best way to do that is to talk about the different colors of the stars, because color is very important to astronomers like me and to people that actually deal with planets around other stars. So why colors? Well, if you heat a metal bar with a torch of some kind, you'll see it will start to glow red. That's red hot. Most people, everybody's familiar with that. But if you heat it even more, you can actually get it to get white hot and then beyond. But of course, the metal will melt by then. So the red is a color and the white is a color. All right. And there's colors in between. So now, and it could even go to blue if we could make it hot enough, but we couldn't. But stars have different colors, and it's temperature related as well. So a blue star is actually the hottest star there is. All right. The red star is the coolest. And it's coolest in temperature, not as in far out, man, cool. But actually, when you see what those stars are, you might actually think they're pretty cool too, as in neato, far out. All right. Well, anyway, if we look at the sun, our sun has spots on it that most of you are familiar with, and those spots are called sunspots. You've seen pictures of them, I'm sure. Well, you're all familiar with them, but what you may not realize is that they are hotter than anything on Earth. They're actually so much hotter than that if they were alone in space, they would glow very, very brightly on their own. But because the sun is hotter, much hotter than the sunspot is, it looks like a dark black spot. It's anything but dark if you had it away from the sun. So it's all relative. Now, when we look at the colors of the stars, we actually determine where they are on this special diagram we use. It's a diagram I grew up with, and I'll try to describe it to you. In 1910, a guy named Ejnar Hertzsprung and Henry Norris Russell, they came up with this correlation that showed that if you put the hottest stars at one end of this chart, and the coolest stars at the other, and then the brightest stars down near I'll tell you this in a sec. It's like the stars they go by color along the x-axis, the horizontal axis. So they go from blue hot all the way just to very low temperature red on the x-axis, the horizontal axis. And then the vertical axis, they go by brightness. So the very dim ones are down low, and the very bright ones are up high on that vertical axis. And the colors relate to the temperature across the bottom, and the vertical axis relates to the brightness, which we'll talk about shortly. And we actually classify stars by measuring their temperature and their brightness. So it's like a little chart. And that little chart has been a leading force in helping us understand the universe for since 1910 anyway, when it first came out. Now, the color gives us something called the spectral class, all right? We know about a spectrum with all the rainbow of colors. So the spectral class, the color, all right, is something that we look for first. But then the brightness, that vertical axis I talked about, that's something else. That's given by something called a luminosity class. And that's just a big word that means how bright is this thing. So together, the spectral class and the luminosity class equals something we call the spectral type of a star. So if you ever see someone say, we're a G2-5 star, that's a G2 Roman numeral V, 5, you'll know what it means. G2 is the spectral class, and the V is the designation for our luminosity class. More in a bit. So the spectral class is a letter designation, and Amanda knows this letter designation, and she'll tell you about it right now because I'm putting her on the spot. Remember it, Amanda?
I do.
Oh,
and we're gonna have to work out another one for the luminosity scale. I've been thinking about that. I'm trying, guys. It would be, depending on your preference, Oh Be a Fine Guy, Kiss Me, or Oh Be a Fine Girl, Kiss Me. It's a mnemonic device to remember the order of the spectrum.
Right. These 7 letters correspond to the first letter of that whole sentence in each of those words corresponds to the letter that we give to these stars. O stars, B, A, F, G, K, and M stars all the way down. So it's O, B, A, F, G, K, M. O, B, A, F, G, K, M. So that mnemonic is something that we were taught when I was getting my astronomy degree. And I just thought it was silly back then until one time when I couldn't remember it. And that was a long, long time ago. And then when I remembered the mnemonic, I realized, oh, that's what it was. I forgot. Now, it goes within each of those letter designations. We actually have a 0 to 9 designator. So we can have an O1 or an 08 or an 06. We could have a G2 like us or a K5. Okay. We can't have an M10 because there is no 10. We can have an M0 or an M9. All right. So in other words, within the letters, there's 0 through 9. All right. So you'll see that shortly as we start to put it all together. Now, so it goes from blue to white to yellow to red in decreasing temperature. So hottest to coolest. So what are the hottest? Well, let's look at the O stars. These stars are on their surfaces are tens of thousands of degrees, and that's in what we call Kelvin. But don't worry about the temperature scale. Basically, it just means it's a temperature scale that starts from 0 because we had to have something where we didn't have a negative number in temperature. There's only 0 degrees Kelvin and going up. So for the O stars, they're bright blue, and they're the hottest stars. They're also many times the most massive stars. You're going to be surprised at how big these are, and I've got some really cool examples to share with you tonight, which I think you'll have fun with. And so they also last only a few 100 million years, right? As opposed to like stars like our sun, which can last 5 or so billion years. Okay, so a few 100 million years is not a long time. And they will end in a very, very violent way. They're going to end as supernovas. And I can explain that later. So an example, right now, if it's clear out, you can go out and look up and see Orion, the constellation Orion. If you look at the belt in Orion, the leftmost star is called Alnitak. And Alnitak is one of these O stars. And it's actually, it's the brightest O-type star in our night sky, believe it or not. And it's 1,260 light years away. All right. And, you know, we talked about time machine during, I think, the last show. And that means that we're seeing it as it was 1,260 years in the past. Now, that star is only going to last a few 100 million years, and then it's going to probably end its life as a massive supernova. So for some future generations, at some point, they're going to see Orion, and then there's going to be a belt with 2 stars and a nebula and a giant cloud of exploded star. So next in our scale comes the B stars. And these are blue, all right? These are not bright blue like the O stars. They're a little less than that, but they're still blue. And they're the next hottest in our scale. Now, they last slightly longer, but most of those massive B stars will also end in this giant supernova, the biggest cataclysm to occur in our universe, other than kilo and hypernovas, okay, which we've heard about recently in the news if you've been paying attention anywhere. Examples are another bunch of stars that are kind of right over your head when you go out right now at this time of the season in February. You look straight up, just about, you're going to see this thing that looks like a tiny little dipper. And those are the Pleiades, the 7 sisters. And they're in the constellation of Taurus, the bull. And the Pleiades are all hot blue B stars, all right? These stars are also very likely were formed all together in a region of space, and then they kind of move together. They are gravitationally sort of bound to each other. So as they move, as they circle our galaxy in their orbit, they kind of go together. They may split off over time, but right now they're together. And there's another thing that's interesting. The stars influence our pop culture, our normal culture, and they also are used as logos for our cars. The Pleiades shows up prominently on the logo emblem for the Subaru. All right, that's what you see there, the 7 sisters on the front. Now, after the B stars come A stars, all right, and they're the next hottest in our line. These are fairly bright, but they're not blue. They're actually white, all right? And they're the first spectral class of star around which planets can form that allow a possibility of any further development. There have been a few planets we found around B stars, but those planets are probably sterile, ultraviolet wastelands. So most likely A stars are probably the place where we might be able to get some planets that actually could possibly support life. An example is the star Vega in the constellation Lyra. That's a summertime constellation. It's part of the Summer Triangle, which is 3 stars and 3 constellations, and the stars are in Cygnus, Deneb. We have Aquila, the eagle, with Altair, and we have Vega in the constellation Lyra. Vega is a very bright star, but it's only 25 light years away. And it's also in the A scale from the OB, AF, GKM. In the A scale, it's an A0. So it's the star that's just past the end of the Bs. All right. And one of the things that we noticed at the star has around it is actually a dusty ring. So this star has a potential planetary possibility down the line. So you have to understand, by the way, that when we watch stars in the sky, we're seeing them at all different times in their history. But the universe, you see, doesn't make solar systems all at the same time. It doesn't make planets all at the same time. It's a sliding window. So we've seen planets that have survived the death of their star, planets that have actually just being formed, like possibly around Vega. and we see planets that are in their full maturity, like our planet Earth. So we see this, and so the universe has this going on all over, everywhere we look, and it's awesome. So moving on now to our F stars. These are whitish yellow, and they're next in our temperature scale. They're reasonably bright, and they can have planets, okay? And there's quite a number that do have planets. Now we move to the G stars, and they're more yellow. Now, they're the next hottest in the scale, so the temperature's coming down. Planets can exist. We know this because we're here. You know, our sun is a G star, so we know that they are present here. We know they can be, and we're a kind of an early G. We're a G2 on that 0 through 9 within the G. Okay, G2, and we'll come back to these. Now the K stars. K stars now are the next line. Now we're getting cooler a little bit, and these stars are orange. And planets can certainly exist around K stars, and they do. Now, we don't know if there's any planets here, but we know that one of the sample stars that we have is Pollux, which is one of the Gemini twins. And Gemini is out, and you can see Pollux when you look up in the sky, the two bright stars, okay, up in the sky. You can look at the stars and see that Pollux is one of those two stars, all right, which is part of Gemini. All right, and then
the coolest of the signs.
You think so?
I think so. But I'm biased.
Oh, you're a Gemini.
I am a Gemini.
Okay, see, now we get it. That's all right.
Don't worry, the nice one showed up tonight.
The nice one? That's good. You better be nice. So then we have M stars as our next line down the line of the temperature scale. And a normal M star, believe it or not, the one that's just fusing hydrogen into helium very slowly, all right? This type of star is the most plentiful star in our galaxy and likely all the other galaxies. It's the most common star there is. There's more of them in the universe than any other type of star. But when you go outside at night, you can't see a single one, okay? Not with your eye, because they're so small and they burn at such a low temperature that they don't show up over great distances. They're not very visible, and that has to do with the luminosity class, which we'll get to later. So it's pretty impressive to see these stars. We've actually looked at a few during SkyTour live stream. We've gone to some M stars. You remember, Amanda? We've gone to a few of these M stars and looked at them. But I think that because of their way, how long they live, they last trillions of years. Trillions. Not billions like our sun, but trillions. Impressive, you know. And most of the planets that exist around these types of stars. And
actually, Bill has a question about just this.
Okay.
He wants to know what type of these class of stars exist in the exoplanets that we're discovering in the universe.
Actually, quite a few. I mean, the actual number, I can get an actual number if we need to, but the M stars are very, very popular, let's put it that way, for planets. And we don't know why, but we do know, okay, that the M stars are the ones that have the most planets around them. Not as in an M star has more planets than another M star. We're saying M stars in general will have the most of the planets. Now, it's also statistics, because there's more M stars than any other type of star. So therefore, we probably are going to, see more planets around such stars. It's sort of a one-to-one thing. And we call those red dwarfs, all right? Just like the show, it was a BBC show I used to watch called Red Dwarf. It was a very funny sci-fi show. Now, as an example, there's one of the places that one of the systems that we found is one called TRAPPIST-1. And I know any of you listening are going, aha, some of you may know this. Aha, I know TRAPPIST-1. I've heard about that. TRAPPIST-1 is a very interesting place. The reason is because it's a red dwarf star. The star is only 0.09 times the mass of our sun. So 9/100ths of our sun. That's so small. And it has 7 planets around it. And all of them are closer to their star than Mercury is to our sun. Yet, 2 of them are in the habitable zone for that M star. Imagine that. You have a day all right, which lasts, if it's a planet that can spin on its axis, you'll have a day that lasts a varying amount of time, but you have a year that's only going to be a few days long, because the planets are so close to the star that they orbit the star within days. We take 360 days, right? 365 days to go around our sun. And Mercury, the closest to our sun, takes 88 days. These planets take just fractions. They only take a few days. There's some that only like 12 days, 7 days, 6 days. It's amazing, how little time it takes for them to go around. But when I mentioned the daytime, how long the day lasts, okay, I was being a little bit cagey with that, because there's something else I want to mention about these red dwarf stars. Most of the planets that we see that are around these stars, all right, are going to be what's called tidally locked to the star. That means they're so close that the same face of the planet will face the star at all times. Now, here on Earth, we don't have that problem. We have roughly a 23-hour day. It's actually 23 hours, 56 minutes, and a couple seconds. But we don't have that problem like this place has, okay? Imagine, though, if you wanted to go view or just go to tropical paradise on one of these habitable worlds, you just go to the sunny side and stay there as long as you want it. The sun's always high in the sky in the same place. It's redder, but you can, because M stars do have ultraviolet radiation they give off. And then if you want to view beautiful sunsets always and take photos always of beautiful sunsets, you just go to the terminator. That is where the sun is always setting. It's never going to change. And so you can spend a week there taking beautiful sunsets every single minute of the whole time. And then if you just wanted to go stargazing, you just cross that and go to the other side. And you end up seeing that. You end up seeing stars and just beautiful skies. So and last thing I'll mention to you, and we're going to go to a break shortly, but let me just say this. When we talk about the size of that star, remember our sun is 865,000 miles across, all right? You can put over 108 Earths, about 109 Earths across the face of our sun. This star is only about 105,000 miles across. So when we talk about this whole star system, it really doesn't, to me, it sounds actually better, more sensible to talk about Jupiter and its moons, because Jupiter is 87,000 miles across. The star is only 105,000 miles across. Jupiter has well over 60 moons, all right? And it makes more sense to talk about Jupiter. Isn't that crazy? I mean, Amanda, when we looked at SkyTour live stream, you remember that we looked at we talked about TRAPPIST-1. Mm-hmm. Yeah, and we talked about these 7 planets, and we talked about just how odd this system was, and we even talked about, it'd be one heck of a paradise. You could actually go there, and if you could buy real estate there, that would be amazing, wouldn't it? Because you could have sunny all the time, or you could say, well, do you want a sunset property, or do you want a sun property, or do you want a star property? Ooh, yeah, it's a tough
star
choice.
Property. That does sound nice.
Yeah, that's something that I would probably go for, but you'd have to be past that terminator just enough so that you have a fully dark sky. Otherwise, you have a permanent twilight, permanent sunsets. Man, can you imagine that? Oh yeah, I'd love it.
Actually, Charles had a question. He wanted to know, would an interstellar civilization choose to retire near a quiet, stable M-class star?
Very good question, because a quiet and stable M-class star is kind of an oddity. And the reason is because they tend to have ultraviolet flare-ups quite a bit. So even though they have the most planets, they also have dangerous ultraviolet radiation that they can spew. Now, that said, I suspect that we will be able, very able to, moderate that if we actually had an atmosphere in the planet, because that would probably protect us. But most importantly, a magnetic field. And you know what? With that, we are up against our first break, Amanda. So I will talk about this more when we come back, and then we'll jump into luminosity classes. So stay tuned. I'm Mark D'Antonio with Amanda on KGRradio.com.
This is SkyTour News for February 4th. I'm Amanda Curran. Today, in 1961, Sputnik 7's failure to launch. Sputnik 7 was a Soviet spacecraft which was to be the first to explore Venus, but 0.8 of a second after ignition, cavitation in the liquid oxygen flowing through the oxidizer pump caused the pump to fail, resulting in engine failure and enabling the craft to leave low Earth orbit. It re-entered the atmosphere over Siberia on the 26th of February 1961, and to avoid embarrassment, the Soviet government announced that the entire spacecraft, including the upper stage, was a test of a heavy satellite which would serve as a launch platform for future missions. A week later, its sister probe, Venera 1, was successfully launched, heading towards Venus, but the telemetry on the mission failed a week into flight. Today in 2002, the International Space Station loses control. After Vesta computers developed communication problems and failed to transfer data to the US gyros on the Z1 module, the GNC MDM computer on the US side stopped stabilizing the station. The computer problems also prevented Z1 from handing over controls to the backup thruster system on Vesta. At 13:18 UTC, the station tumbled, in danger of losing electrical power, and experiments were shut down as systems were put into emergency mode. The crew were able to manually point the US solar arrays, preventing any loss of power. The station restored to operations later in the day, with altitude controls resuming at 1843 UTC on thrusters and 1920 UTC on gyros. Today in 2004, the Ulysses spacecraft makes its closest approach to Jupiter. The primary goal of the Ulysses mission was to orbit the Sun and to study it at all latitudes. To do so, the probe needed to change its orbital inclination and leave the plane of the solar system. To reach the desired orbit around the Sun, a gravity-assisted maneuver around Jupiter was chosen, and during Ulysses' second approach, it was able to make its closest observations at 0.8 astronomical units. This was SkyTour News. I'm Amanda Curran.
Hey, welcome back to SkyTour Radio. I'm Mark D'Antonio with host Amanda Curran, and she's still here, right, Amanda? She's there. I can hear her from now.
Still here.
There she
Still
is.
here.
Yeah, here we are at KGRAradio.com, and I wanted to just give one reminder. On the FX Models Planetary Replicas Facebook page, and the link is on the KGRA Radio show site for SkyTour Radio. If you purchase any items in our store, you can get a $15 discount. All you have to do is enter the code SkyTour15. That's SKYTOUR15. There's a limited time offer, and you can get 3D printed craters and features from the Moon, Mars, and even Pluto. And we also have the History Maker series of UFO models that represent historically significant UFOs. Now, whether these UFOs are real or imagined doesn't matter. They had a significant impact on our history and our culture. And so we made them available. Series 1 is now available in the store. So if you're interested, head on over there and enjoy. Now, we were talking about TRAPPIST-1 and the amazing solar system that exists there. It's like a 7 planets that are closer to their star than Mercury is to our sun. That's just an amazing place. And we talked about how those planets might actually be tidally locked. That is, one face of those planets always faces the sun, their star, just like our moon always faces our Earth. In future shows, we'll talk about our moon and how it relates to the Earth and the types of things that it causes here and doesn't cause here. So that said, moving past the TRAPPIST-1 system, which is really incredible, let's talk about now the second aspect of star classification. We talked about the spectral class, which is the O, B, A, F, G, K, M colors, right? And those are related to temperature. But now we talk about luminosity class. Now, what is that? Well, the luminosity class is the classification from the largest to the dimmest, right? And that is the biggest to the smallest stars, the largest in brightness to the dimmest in brightness, okay? And each luminosity class is something called intrinsic brightness for the star. It depends on the radius of the star, among other qualities. Now, you can imagine when stars form, they can have very small sizes, like we know in TRAPPIST-1, or they can have very large sizes, like Rigel and like Alnitak, stars that are in Orion, for instance, and more. Now, these stars have such incredible differences in size. Now we're going to have some fun, okay, as we go through these luminosity classes. You don't have to remember all these luminosity classes because we'll put them out there, okay, and you'll see them. They might be on their SkyTour livestream companion site, or we'll make it as part of a new video for the show. But let's start off with the biggest stars in the universe. These have a designation called, and it's Roman numerals now, Roman numeral 1, little a, O. So these are the 1AO. These are hypergiants, the largest stars in the universe. If you can imagine, these stars are 1,650 times the diameter of our sun. Okay, the sun is 865,000 miles across, as I mentioned before, or over 100 plus Earths across. Now, let's do a little scale here. And I did this because, as I mentioned to you before, I wrote a program to do all this, calculate special sizes of the sun for certain conditions. If the sun was 1 inch in size, 1 inch, these hypergiant stars would be nearly 137 feet across if the sun was 1 inch. Just imagine that. That's the size of a star. That's immense. Now, on our scale here, where the sun is 1 inch, that would put the star well past Saturn, which would be at 86 feet from our 1 inch sun, and nearly to Uranus at 172 feet. All right, 137 feet. That's just in our model. Now, we also have in our next luminosity class, we have what are called the 1As, and these are luminous supergiants. These stars are about 1,000 times the diameter of the sun. So if we had a 1 inch sun, okay, those would be about 83 feet in diameter. That's still pretty big. So now in our model, that's so close to Saturn at 86 feet away in our model that planet would be evaporated before the star even started commencing nuclear fusion, okay? It would be too hot already at that distance. The next level in the luminosity scale are the 1Bs. These are less luminous supergiants, all right? And these stars are sort of a middle tier, and they're somewhere between the 83 feet and maybe say about 30 feet in diameter. And then we have the compared to our 1 inch sun, and then we have the type 2, and these are again Roman numerals, so II, 2. These are the bright giants, and they're exceedingly bright. They're from 30 to 80 times the diameter of our sun. Now, for the 1 inch sun, that means that the largest one of them would be about 7 feet in diameter. Now, that's out past Mercury on our scale model, and Mercury is at 3.4 feet, and it's actually past Venus, which is at 6.5 feet, and is nearly to Earth, which will be at 9 feet. All right. Now, you'll remember some of these, and you may not remember all of them, but again, we'll make them available here and there in some different places and some of our different SkyTour locations. Now, there's a type 3, which is III, the Roman numeral 3. These are giants, and they're about 50 times the diameter of our sun. So imagine with our 1 inch sun, imagine a 1 inch ball and then a 4 foot ball. 4 foot ball. I'm being careful not to say football right now, Amanda. You can see what that could cause right now, right?
The Patriots just got a touchdown, apparently.
Uh-oh. All right. I'm not going to even go there because there's Eagles fans who are listening and there's Patriots fans that are listening. Anyway, at 1 inch in diameter for our sun, the giant stars would be 4 feet across. That's past Mercury at 3.4 feet. Okay, not quite to Venus at the 6.5 feet in our scale model. Right. Now we come to this magical spot called not yet, not the magical spot yet. There's one more class I got to talk about, and that's the Type 4, okay, IV, the Roman numeral 4 subgiants. These are brighter than the next class that's below, but they're actually they're not quite bright enough to be one of these giants, but they're also not small enough to be something that is in the class that comes next, which is the Type 5, the V. Okay, there's enough subgiants to warrant another luminosity class, which is why we have a type Roman numeral Type 4 subgiant class. All right, and so in the 5 class, Roman numeral 5, this is normal hydrogen fusion class. This is what we call normal stars. Examples, well, we know one right away. The Sun. The Sun is a G2 spectral class, and its luminosity class is Roman numeral 5. So we say, just to make it a short, we say it's a G2-5. Okay, G2V. All right, G2 Roman numeral 5. So now, if we look at other stars like this, Sirius, the brightest star in the sky, also visible if you go out at night, on any clear night right now during the winter. Sirius is to the left of Orion, and it's a very bright white star. It's an A0 or an A1, depending on who does the classification. And as the brightest star in the sky, it's also a normal hydrogen burning star. And it's only just a few light years away. It's not even far away. It's like 8 light years. And it's like an A0 or an A1 5, Roman numeral 5. Now, there's something else too that's interesting about Sirius. It has a small companion star to it that you can't see without a powerful telescope. And we'll talk about that little companion shortly. Another example of a normal hydrogen star, and hydrogen fusing star, is one we already talked about, and that's Vega. It's in the constellation of Lyra, which is in the summertime sky, and in August it's right over your head. And that's an A0 Roman numeral 5 classification. Okay, Vega is actually kind of cool. We use Vega in astronomy as a what we call a standard star. It has a spectrum. When you take its light and you spread it out into the colors, you can see all kinds of features within those colors. Those features are called absorption lines. They're dark little bands that you see, and they're in characteristic places. Now, every star has these. Our sun has a whole bunch of them. In fact, our sun actually has so many of them that they look like the sun looks like it has its prismatic view with tiny little bands all throughout it. Like looks like hundreds of them, and that's just about how many there are. And these bands are due to material that's in the atmosphere of the star. And this nomenclature that we use, like this A0 and Roman numeral 5, it kind of gives us a lot of info about the star. It kind of gives us a rough idea about the temperature, its size, the processes that it's using internally. All right. And when you look at the spectrum, you see some expected results for the particular class of star. All right. That's kind of interesting. Now, this luminosity class 5 we're talking about, Roman numeral 5, it has a special place on that HR, that Hertzsprung-Russell diagram. Remember that Ejnar Hertzsprung and Henry Norris Russell created. When they did that mapping, they found that there was a bunch of stars that had a position on their diagram that sort of snaked from the upper left down through the middle and then down to the lower right, kind of in a fairly straight line, a little bit of a curve to it. And they realized these are the normal stars, and they're called the main sequence. It's the main set of stars, the main stars doing normal hydrogen fusing into helium. All right. Now, depending on the mass and temperature of the star, you can exist anywhere along that temperature and color diagram, along that Hertzsprung-Russell diagram. So it would depend on its radius, all right, which is that luminosity, part of the luminosity class we talked about, and its temperature. So, for instance, we talk about a blue supergiant like Rigel, all right? Rigel is a supergiant. Rigel's in the constellation of Orion, and it's a B2 1A supergiant. That is B2 Roman numeral 1 little a. Okay, that's one of the classes. Remember 1A. And the 1A luminosity class says it's a supergiant. And that means that if we put the sun at 1 inch, Rigel would be 13 feet in diameter. So in our model, Mars is sitting at 13.5 feet away from our 1 inch sun. And at that scale, Rigel would eat up every single planet in our inner solar system and even probably destroy Mars as well. Isn't that huge? I mean, that's massive, you know? So when we're talking about these luminosity classes, okay, they specify really the size of the star because of the brightness of the star is typically, going to be much, much brighter the bigger it is, all right? So I think that's sensible, Amanda. What do you think?
Oh, I think that's sensible. Sorry, I was just trying to post a picture of Orion's belt, and it doesn't look like it went through, so...
All right, well...
Trying to give people a bit of an idea of what you're talking about, but it didn't have Rigel in it, though.
Rigel? Yeah, okay. That's all right. All right, well...
but, see, is there a mnemonic device for the luminosity scale? Because I didn't realize they were Roman numerals. I thought they were L's. And I saw an outline of the spectrums and luminosity, and I thought L. So I just saw it scroll by and me.
Tell them what you thought. Tell them what you thought.
I thought it said something about obla de obla da, and I didn't, because it was just a bunch of random letters, and I thought the Roman numeral 1 were L's. So I'm seeing like O, L A, L B, and I'm like, what is this? I'm like, did he figure out a way to like tie it into the Beatles to help me remember? But it's not. It's eyes. But is there a mnemonic device to remember luminosity though, or?
No, and the reason there isn't is because the luminosity classes, more so than the spectral classes, have actually been relatively stable throughout our history in astronomy. I'm sorry, the spectral classes have been relatively stable, and the luminosity classes have changed here and there. For instance, after the Roman numeral 5, which is the normal hydrogen fusing stars, which by the way are called dwarfs. Okay, if a star like the sun is called a dwarf, I guess it makes sense when you look at what the other stars are for their size. I mean, you have Rigel, is a supergiant, and it would eat up everything all the way out to Mars if it was placed there. So if it was placed at the sun, so clearly it doesn't. The sun is somewhat of a dwarf, isn't it? Relative to Rigel, but there is a class of subdwarfs, and that's luminosity class Roman numeral 6. These are stars not quite massive enough to be in that Roman numeral 5 class, and they primarily do hydrogen fusion as well, but they're set apart from the type 5 luminosity class by various qualities. Typically, and this is something that none of you have to remember, but it has to do with the amounts of elements in their spectrum other than hydrogen and helium. Okay, if they're low, they might be a subdwarf star. Okay, that is to say, and we call those any element other than hydrogen and helium to us astronomers is called a metal, which makes no sense. You can say, well, wait, come on, how is oxygen a metal? Well, it's not. But in terms of the other fused elements that are in a star's spectrum, hydrogen and helium are the primaries, and everything else we call metals. And some of that will make sense perhaps in a short time. Now, the last luminosity class is an odd one. It's WD. Now, what's that mean? WD means white dwarf. Now, if you remember, that's an end state of stars around the sun size. Okay, if you know that about that. If you don't know about that, then you remember that we talked about Sirius, and it had a companion. Well, that companion's a white dwarf. So that means that it was a normal star at one point. Sirius had another star next to it that was probably of substantial size, and then it went down to a white dwarf stage. So Sirius has not always been the brightest star in the sky. The brightest star in the sky was that tiny little white dwarf once upon a time, a long time ago. So that's pretty cool. Now, we want to talk about where do these stars come from? and how are they made. But before we do, I just want to turn it over to Amanda to see if she has any questions, if anyone has any questions out there, because I am very interactive, and I do like to solicit questions and hear from the people watching in the chat or people that would like to write in questions.
Yeah, and actually you read my mind because I thought that was going to be a good break for a question that came in. Kind of pertains to last week's episode, but I saw something on Facebook and I meant to ask you about it and I forgot, and this person's question reminded me.
Okay.
Loki wanted to know, like we were talking in chat about like the light being from the past, like looking at space is like looking at the past. Do you know what I mean?
I do.
I'm
Yeah.
not phrasing it as elegantly, but
That's okay.
if we saw light from a certain distance, I'm gonna butcher this. We would be looking back in time because of the light year, like 8 minutes from the sun. The light from the sun to Earth takes 8 minutes. Do you know what I mean?
Yes, it does.
Okay. If that was the case, if there were any intelligent beings out there looking at us, would they be seeing us in the past?
Oh, that's a wonderful question. And there's various science fiction shows that actually tackle that, and they show societies that actually modeled themselves after what they saw of Earth. Now, how could they observe the Earth and see the actual goings on at that level? Yeah, obviously, that's science fiction. That's why it's called science fiction. But if you went out 100 light years, all right, 100 light years, and you look back at our Earth, you'd see the Earth as it was 100 years ago, all right? And that is very true. You would see the old Earth. You wouldn't see the current Earth because the light, I mean, if you were traveling out and you turned around and looked back, you're traveling. Let's say that you appear out there. Well, never mind the travel time because that throws into complexity that's not even important. But if you just were out there, you just like materialized out there and looked back, that's exactly what you'd see. You'd see the old Earth. And if you were actually across the galaxy, say 150,000 light years away, and you managed to close in on the Earth with your massive multi-dimensional telescope or something, you would actually see Earth as it was 150,000 years ago. And so you wouldn't see any cities, you wouldn't see people running around, you wouldn't see any of the stuff that we have now. So this is why we said in the last show the universe is one big giant time machine, isn't it? See?
Okay, that's crazy because the thing I saw it on Facebook, so obviously I didn't believe it, but it was just a really cool concept. It said something like if you went far enough out and looked back, you'd see the dinosaurs. Or not far enough back, but like someone looking out. And well, I thought, well, I don't know if that's true, but what an interesting concept.
Yeah, it is a concept that's really cool. As a matter of fact, if you wanted to go back and see the dinosaurs, you'd have to go out. Well, you'd have to literally go as far away as some of the galaxies, some of the farther galaxies. You'd have to go out 70 million light years.
Okay, okay, saying go out.
Yeah, in other words, let's say if you had a civilization that was already out there
already, yeah, because we wouldn't be able to leave Earth.
Right.
Like if we made that, I can't remember what it's called, but to get to Alpha Centauri.
Yeah, the warp drive, the Alcubierre drive.
Yeah.
Yeah.
Would we actually be able to do that? Would that be our way of? It wouldn't really be time traveling, but.
No, but if you went out and let's say we left from Earth, just to add total confusion to the mess. Let's say you left from the Earth and you went out to Alpha Centauri, which is 4.3 light years away. That's the system, and the little red dwarf star, M-type star that we talked about, which actually has a planet around it. Okay, that we noticed, we found. Let's say you went out there. Now, if we used a warp drive like Miguel Alcubierre came up with in 1994, and which NASA is now funding research for, because it's realistic now that they reworked it. If you went out there and you did it, say, in 2 weeks, and then you turned around and looked back, you could literally look back, and you're going to see light that took 4.3 light years to get to you. So you could actually look back and see your ship being constructed in orbit before you ever left. Okay, because you
Okay,
only
that's
went.
hard to wrap your mind around. That's
I know, but
crazy.
think about it, because if you get there in 2 weeks, the light coming to you from there, once you stop and you look back, the light coming to you from Earth is 4.3 years old. And if you left 2 weeks earlier, well, your ship got finished and off you went. But you could see the state of construction of the very ship you're looking at Earth in, okay, in orbit around the Earth if you had a powerful enough telescope. You could actually see it under construction in Earth orbit. All right. And
Wow.
that's the crazy part, right? Because remember, we're not getting there we're not taking 4 years to get there. We're not traveling at light speed. We're circumventing light speed when we actually use what they call the warp drive. We're folding space. So if you imagine the opposite corners of a piece of paper, the upper right piece of the edge of the corner and the lower left piece of the corner, imagine folding those up and close to each other. All right. That's the distance you traverse between those 2 points of those corners. If you unfold it and you measure the distance between the lower left corner and the upper right corner, you get a diagonal distance of some amount. Okay. If you fold those corners up together, those same 2 corners that were previously so far away are now right next to each other. That's, in effect, that's the principle of the Alcubierre drive. That is true warp drive, in a sense, because we're actually warping space, perhaps, or folding space. That is, folding the space-time continuum. I mean, I love saying that word, that phrase, space-time continuum. It sounds like you're part of every science fiction movie ever made, because no matter what it is, they always mention the phrase space-time continuum, and you always have people that talk about it, but they don't even know what it is. Okay, and that's okay. But if you could fold, and they say, well, how can you bend space? Won't that rip up everything around the Earth if they just did that? The answer is no. And the reason that it doesn't do that has to do with Einstein's theory of relativity. And more importantly, within there, it has to do with something called a reference frame. Now, somewhere out there in the audience, someone's going, aha, yes, I know that. I know about the reference frames. Because there are people that listen who are nerds like me. I'm a nerd, okay? I admit it freely. And so if you look at that and say, well, you fold those corners up, okay? For your ship, you have made this fold in space. But on Earth, someone watching you in Earth orbit would just see your ship, once it's activating its warp drive, would just see the ship disappear. Seemingly impossible to do, because we don't know anything that can go invisible instantly. But if you're actually circumventing normal space, then you will actually seem to shimmer perhaps and disappear. And the next thing you know, the next notification you get is after they winged past Pluto a couple seconds later, or not even, probably just a short time later. So then you say, well, how did that happen? They're going faster than light. Well, the answer is they're not going faster than light. They're actually not utilizing the normal universe. They're in the warp bubble. And the warp bubble is a concept that's beyond the scope, I think, of our show. But it's something that is a construct that was theoretical until it wasn't. And this is something that, like I said, NASA's investigating this now. The Alcubierre drive used to require a lot of energy. In fact, to create that warp bubble, by the way, don't exist naturally in space, in the universe. So we'd have to make it. And to create the warp bubble, we would end up having to literally convert a planet the size of Jupiter to pure energy to make a warp bubble. So it was a stupendously, colossally impossible thing for us and probably any other civilization. So by reworking the little shape of the ship, they managed to figure out that they could actually reduce the energy requirement to something that was the equivalent of the Voyager spacecraft converted to energy. And now it became practical, potentially. And NASA's looking at it now. Now, we only have a couple of minutes left, but I did want to mention to you, remind you one last time, if you go to our SkyTour radio page on KGRA, you will see that we have some links there. Those links will take you to, among other places, the FX Models Planetary Replicas page on Facebook. If you purchase any item in our store right now, we have a deal going until this coming Wednesday. You enter our code SkyTour15, SKYTOUR15. It's a limited time offer, but it'll allow you to buy anything in our store for $15 discount, for a $15 discount. All right. So you can get 3D printed craters from the moon, Pluto, even Mars. Okay. You can get any of our UFOs, any or all of our UFOs we make. There's the History Maker series is a series of 3, and it's a series of little UFOs on a stand with an embossed plate that tells you which ones are which. All right. And there's significant UFOs in our history. And now I'll turn it over to you, Amanda. You can tell us what's coming up next.
Up next, actually, we have Let's Talk Paranormal with host Tracy Austin. So do look forward to that.
That sounds fun.
Not sure if we have enough time for another question, so we are going to hold that one over for next time.
All right. Well, then, for me and for Amanda, I want to thank you for listening. And I did very well avoiding talking about football, didn't I?
You did.
Good.
I don't know if it's over or not. I wasn't paying attention, but I'm really pleased to see a lot of our good friends showing up in chat to be with us rather than football.
Awesome. Well, thank you guys, the ones that did show up. Thank you so much. The ones that listen in the future, I'm still grateful that you listen. You know, on behalf of Amanda and myself, I want to thank you for coming to SkyTour Radio here on KGRA. I'm Mark D'Antonio, and that's Amanda Curran over there somewhere.
Up here in Canada.
and in Nova Scotia. Hey, so listen, we'll talk to you later. We'll see you next time. Thanks for listening.
Have a great week, guys.